gets an understanding, it might be worthwhile to try and keep all sort of questions except sort of burning questions of clarification until the end. I'm going to try and go through things. Hopefully it'll spark a little bit of conversation, and we'll be able to chat a little bit about how the world of game theory comes into practical use at the end. If there's anything as I'm going through the slideshow that is a burning question of clarification, please feel free to raise your hand, and I'm very happy to take questions as we go. But yes, with that, I think it's probably time for me to get going. And I think possibly the first thing that I'm going to start off with is something that you might not expect. I'm going to start off by talking to you about the ice caps and our climate crisis, where I'm going to tell you that if you have a look at this graph that shows the carbon dioxide parts per million in the atmosphere, you can see that 800,000 years before today, if you're looking at the levels of carbon dioxide, they've stayed fairly low. But all of a sudden, we see not that long ago, maybe 20,000 years ago, things started to increase. We start to see an increase in carbon dioxide levels, and we see that between 1911 and today, we've just seen this absolutely massive uptick in carbon dioxide levels in the atmosphere. Now, I'm sure this isn't news to anyone, but coupled with this uptick in global carbon dioxide levels, we also see this massive decline in the amount of ice that is, the ice surface, the ice mass of Antarctica. So if you have a look just from sort of 2003, 2004, if you're having a look, this is where the ice cap mass started, and we're seeing a huge decline in the amount of ice that is sort of sitting on Antarctica and Greenland's mass. If we want to think about it, I mean, our global temperatures have risen by about 1.36 degrees Celsius since about the 1850s, and that's led to us losing ice cap mass, and that's of the order of 440 billion tons of ice per year. And 440 billion tons it's a bit of a funny number to try and get your head around. So if you think about the fact that your average car weighs about 2 tons, and there are approximately 7.9 billion people in the world, the amount of ice that's coming off Antarctica and Greenland is the equivalent of each person in the world owning 28 cars. That's the amount of weight that's coming off Antarctica and Greenland. Or if you want to think about it in terms of South Africa, it's every single person in South Africa having the equivalent of 3,667 cars. I mean, I don't think I can overstate the crisis that we're facing in terms of how much ice is coming off these polar caps and Antarctica and Greenland, and we can see that this is an issue that we're facing, in a modern, contemporary setting. So, now that we understand this problem, the question arises as to what do we think we actually want to do about it? So how might we go about dealing with this climate crisis that we're facing? On the one hand, we might think, oh, you know what, we need to take some serious action. We need to start, I don't know, recycling, reusing. We need to start thinking about the environment. We need to take the Paris Agreement, for example, climate accords, things like that on hand. We need to start thinking about renewable energy sources. How can we minimize our carbon footprint on the world? On the other hand, we could be thinking, you know what, let's just carry on as usual, right? I mean, it's too much effort for us to change things, driving our car, trying to change to an electric car in South Africa with load shedding the way that it is at the moment, absolute crisis. We're never going to be able to do it. Single-use plastics, we may as well carry on using them because they're cheaper. And what really does one extra bottle do in the grand scheme of things? So we might be thinking about the climate crisis with these two slightly different approaches in mind. Do we take the climate crisis quite seriously, and do we decide that we're going to actively do something about it, like, going green, for example? Or on the other hand, do we think that we want to just carry on with business as usual, carry on in the world exactly as it is today? So you might have your own opinions. You might feel very strongly one way or the other, and that's completely fine. Different people will have different opinions. But sometimes you might, or at least you might be thinking, what on earth does this climate change scenario have to do with game theory or economics, or did you accidentally come to the wrong masterclass? Did you come to this class thinking that you were going to learn about game theory or something to do with economics, and it sounds like you've accidentally walked into the latest sort of geography class where we're learning about pollution? And so what I'm going to say to you is that climate change, as we understand it, we can model it as economists as something called a social dilemma. Now, a social dilemma is really just a fancy term for a situation where there are various agents or people involved in an interaction who don't consider how their own personal actions are going to impact on the well-being of others. So the minute you've got a situation where people are taking decisions and not thinking about how their choices impact other people, you could end up in a social dilemma. And this is where we start relating to economics, because in economics, a lot of what we're doing is making decisions about how much we're going to consume, what we're going to consume, how to maximize profit, but we never really think about the other guy. We never really think, well, if I do this, how's it going to affect the other person, right? And game theory tries to bridge that gap. So, for example, if we have a social dilemma where, like climate change, where you end up making decisions that lead to the overexploitation of some kind of common resource. So, for example, like overexploiting the atmosphere, we could end up with what we call a tragedy of the commons. And it was in about 1958 or 1968, I forget the exact date, that Garrett Arden wrote a paper called The Tragedy of the Commons, where he basically explained this notion that if you've got a communal field and all different farmers are trying to fatten up their cattle for the market, if you let every individual farmer fatten up their cows as much as they want, they're going to end up eating the entire grass, the grass supply. You're going to end up with fallow land the following year because you're not going to be able to grow grass again. So individual behavior can lead, or individually selfish, individually self-interested behavior can lead to the overexploitation of a common resource. And these social dilemmas and tragedies of the commons are things that we experience even today. So it doesn't have to be this arcane example of a field out in the middle of nowhere that is shared by a whole bunch of farmers. In fact, traffic jams are an example of a social dilemma or a tragedy of the commons. Everybody wants to take the freeway in Cape Town to get into the city because it's the most direct route, but every individual person that gets onto the freeway adds traffic and ends up extending the commute for everyone else. Their actions have impact on other people that they don't necessarily think about when making their choice of how to get to work in the morning. Stacking up dirty dishes. I'm sure we've all had that experience, or we might be the one who, when we have to try and clean up after supper, we stack the dirty dishes in the sink rather than washing them because, it'll be easier for me to do it tomorrow. But what about everyone else that's staying in the house with us? What about, mom, dad, granny, husband, wife, anything like that? What about those people who now have to live in the dirtier environment because you chose to take an action that was easier for yourself? And I think possibly the most recent one that comes to mind, and possibly the most contentious one, and I don't want to open up a can of worms here, but the vaccination against disease, particularly COVID-19. Think about the arguments that people had about why everyone should go and get vaccinated. Think about the herd immunity arguments, why we should be going to go and get vaccinated. And even if we knew that there were some very small risks to having our vaccinations, why should we be taking those risks? Because it's actually for the good of everyone else around us, right? We have these positive effects on other people. And if we don't consider that, we might end up experiencing a tragedy of the commons where we exploit the public health system, and it turns into a problem in general or for the society at large. So we know that we've got these tragedies of the commons and social dilemmas that crop up every day. But the one thing, it's not all doom and gloom. As you've probably picked up, I mean, South Africa has managed to do an awful lot of vaccination over time. You know, we've managed to get our vaccines going. We've managed to try and change the way we behave. You know, you might have conditioned your partner to pack the dishwasher rather than leaving things in the sink. And as humans, we have actually found ways to solve these social dilemmas, engage in these social dilemmas, and try to steer them towards the outcomes that we want for thousands and thousands of years. So, you know, all the way back 2,500 years ago, Aesop, who wrote the story about the tortoise and the hare, wrote a story about Belling the cat, where there are a bunch of mice who are living in a house with a cat, and they know that this cat is dangerous. They need to do something about this cat. So they decide they're going to tie a bell onto the cat's collar. The problem is, one of the mice is going to have to do that. And so individually, the mice wouldn't want to go and tie a bell onto the cat's collar, because one wrong move and they become mouse on toast. And it's time for them to, you know, meet their maker. They're done for. And so it's the ultimate sacrifice for other people. And that goes against the sort of traditional economics notion of you do what's best for yourself. You look after number one first. But Belling the cat is this fable that Aesop came up with, where he says one of the mice might be willing to take on an action that is self-sacrificial or altruistic in order to solve the problem of the mouse colony being in danger. Because if they can tie the bell on the cat's collar, they get the early warning system of the cat is on its way, they need to hide, right? Other examples that aren't from the world of fiction. So in Spain, for example, we've got the Tribunal de las Aguas de la Valencia, and this is just basically a water court. So in one of the water scarce areas of Spain, a bunch of farmers get together and they monitor water usage by their peers. And if anybody is found to be using too much water, they get reported to the Tribunal de las Aguas, and this tribunal essentially metes out punishment on people who are found to not be acting in the interests of society. So we found a way to monitor and assess people's behavior and to try and get them to conform to ways that we want them to behave instead. Another example is the COVID-19 pandemic. We've already sort of touched on this, where there was the social dilemma of there's this virulent spread of, or there's the spread of a virulent virus. We need to make sure that it stops its spread, or at least if it does get spread around, that people are protected against it. We need to protect other people. So we encourage a whole load of people to go and get vaccinations, to flatten the curve, to try and help our healthcare systems, etc. And so all of these examples talk to us about a situation where there is a problem of some description. We've got some situation where individuals behaving in their own interests might not necessarily lead to an outcome that we want. So there's some kind of tragedy of the commons, there's a social dilemma, there's some kind of problem that we're facing. And we realize that we actually do want to change this up. We don't want to end up in a situation where all the mice have been eaten. We don't want a situation in Spain where all of the water is actually being used up. We don't want a situation in the COVID-19 pandemic where our hospital, particularly in South Africa with a frail healthcare system, where our hospitals and healthcare systems are crumbling because we haven't taken the requisite measures to flatten the curve. So this is where game theory comes in. Understanding how people interact with one another, right? Game theory is the study of basically people interacting with one another, and those interactions, whether they be social dilemmas, normal interactions, whatever they might be, they are what we would call a strategic interaction. And a strategic interaction is just something where you've got a scenario, there are two or more agents, and they interact, and they know that whatever decision they make is going to have an impact on other people. Now, you might have started to touch on this if you've done some of your basic economics. You might have heard about externalities, spillover effects, things like that. And that starts to touch on this. And I suppose this is where the theory of game theory kicked off, right? Is that we know that sometimes our decisions can have impacts on other people. So we've got to start thinking about how our decisions impact other people and vice versa. And that is a strategic interaction. We know that if I choose something, it's going to impact you. And I know that if you choose something, it's going to impact me. And we have to come to some kind of agreement between us. It doesn't have to be a formal agreement, just some kind of tacit agreement as to how we're going to act, knowing that we impact on one another in our action choices. So what I'm saying here is that agents' behavior ultimately depends on both their own and others' actions, or their perceived action. So if I think you're going to do this, then I will behave accordingly, as well as the preferences that I hold. So do I like living in a clean environment? Do I like having a healthy community? Do I like having water available in my taps? Things like that. And what are your preferences? Do you like the same things that I do? Do you like different things to what I like? All of that. And what we do is we use game theory basically as our mechanism to study these strategic interactions and behaviors to understand how different people might behave in different ways in different scenarios. So game theory, I mean, it probably has one of those names that sounds a little bit like you're going to be studying computer games or something like that. But really what we do is we say that a game is just a strategic interaction between people, and we want to put it into some kind of model. We want to understand human behavior in some way. And so we say, right, well, let's take an interaction between people. Let's say this interaction that we're having right now, me presenting something to you. This is an interaction that we could analyze using game theory. But in order to actually activate game theory or to utilize game theory meaningfully, we need to have a certain number of components. We need to understand certain aspects of the interaction to be able to meaningfully put it into a model. For example, some of the things that we need to build up a game are the players. So we need to know who is involved. Who are the people that are actually getting involved in this interaction? Who is going to be playing this game? Who is in the strategic interaction, right? In the example of this particular environment where I'm presenting to you, the players are myself and you, right? You as the audience are players in this game, in this interaction. So we need to be able to essentially identify who this impacts, who are the people involved. We also need to understand the strategies, and this is what plans of action are open to the players. So in this scenario, what could I do when I'm presenting this class to you, when I'm presenting this lecture? What are my options? I could present something very quickly. I could do a perfunctory sort of reading of my slides, or I could choose to do something a little bit more engaging. You know, the choice of this being on Teams versus in person is also a game theoretic decision. You know, we make the choice to put this on Teams rather than in person because of the kinds of impacts it'll have on you as the audience. It'll reach a wider audience, but at the cost of potentially some interaction, right? So we know that choices we make about how to present, what we're going to be doing, that's going to have impacts on the people around us. And we need to know what are those actions that are available to us so that we can understand the different choices that we can make. Another thing we need to understand is what we call the information. So we need to know, what does each player know when they are making their decision? So what do I know about this interaction coming into it? Do I know how much everybody knows about game theory? Do I know how interactive my class is going to be? Do I know how many people are going to be joining us for the lecture, right? Things like that. You also coming in here, you don't know me from Adam, right? I could be a terribly boring individual that, I'm very, very uninteresting. It could be a waste of time where you could really have been spending that time watching a new episode of a series on Netflix that you're enjoying. So you don't know everything coming in. I don't know everything coming in. But we need to have some idea of, well, what do we know? Because once we understand what we do know, we'll be able to work out how exactly this game gets modeled. Is it a simultaneous move game? Is it a sequential move game? Is there risk? Is there uncertainty? All of those kinds of things come in here. Right, and this is my point here, that we use information to classify simultaneous versus sequential move games, and I will come back to this point in a moment. The final thing that we need for a game is payoffs. So we need to basically understand what an agent's happiness or utility will be under each possible combination of outcomes. So how happy will each outcome make each individual player? So onto this sort of simultaneous versus sequential move game, there are two main classes of interactions that we have. One is a simultaneous move game and another is a sequential move game. I'm going to zoom through this, but just the idea is simultaneous move games are ones where our agents move with the same amount of information. It doesn't necessarily mean that they have to move at the same time, but it means that you don't see what I've done before you choose what you're going to do. Right, and we often represent these games in tabular form, game tables, or what we call in the sort of technical terminology, normal form. Examples of this could be something like rock, paper, scissors. If you studied your higher level economics, you might have heard of Cornerstone market pricing games. But rock, paper, scissors, you don't know what your opponent has done when you choose rock or paper or scissors, or lizard or Spock if you're a Big Bang Theory fan. But you don't know what your opponent has done, so you're making your choice with the same amount of information as them who don't know what you've done. Sequential move games, on the other hand, are games where agents move with different amounts of information. So, for example, one agent will make a move, the other agent will observe what this move was, and then they'll choose their best response as a sort of response to what's happened. They've seen what's happened, processed it, and they make their choice about what to do from there. So these are often represented in what we call tree format or game trees. Technically, they're called extensive form. You might have heard about, games of chess, right? Chess is a sequential move game. The player with the white pieces moves their pawn forward, and then you see how they've moved, and you make a choice about how to respond to that. The player playing with white will then make a choice to respond to how you've moved your pieces, etc. So it's constantly updating the amount of information you have in order to change the moves or the actions that you take. Other examples are Stackelberg pricing games that you might have heard of in your economics courses, or alternating offers bargaining. So, the sort of, I put something down on the table, you don't like it, you make a counter offer, I make a counter offer, etc. That's a sequential move game. Just to give a very quick overview of the two different forms of games, this on the screen is a simultaneous move game, and this is what I mean by the sort of tabular or game table form. This is how we would represent it in a sort of technical format. You can see that I have labeled different players. We've got player 1 and player 2. The 1 is what we call the row player because they are on the rows, and the 1 is the column player because they're on the column. You can see that player 1 has some strategies. They can choose to do strategy X or strategy Y. Player 2 has some strategies. They can choose to play strategy A or strategy B. Now, these cells, for example, I see that the logo is slightly covering my block, but this cell over here is the cell that represents where player 1 has played strategy X and player 2 has played strategy A. So that is a cell representing a particular outcome, right? This cell represents another outcome where player 1 has played strategy Y and player 2 has played strategy A. And all of these different cells represent the different possible outcomes that we have in the game. And we'll label the cells according to the convention row name, column name. So it's like labeling an Excel spreadsheet in a way, right? And then the numbers in the cells are the payoffs that represent agents' utility, so represent their happiness in each scenario. So if player 1 plays strategy X and player 2 plays strategy B, then we say the blue payoff, or the first payoff in the cell, will represent player 1's utility, and the second payoff in the cell will represent player 2's utility. So in this particular scenario, player 1 will get a payoff of 4 and player 2 will get a payoff of 6. And this represents a simultaneous move game where players, for example, are playing rock, paper, scissors. They don't know what the person before them did, right? On the other hand, you've got a sequential move game where players do know what's happening. And this is the tree form that we represent sequential move games in. And we start off with these dots, which are called nodes. A node is just basically a fancy word for a point where actions get taken. So at this circle up here, somebody needs to take an action, and we label it to say, well, player 1 is our first player who will take an action at that point. The actions that player 1 is able to take will then descend from that node, right? So action A and action B are player 1's actions that they're able to take from that node. These are, in essence, like player 1 strategies, right? Then player 2 will be moving at these nodes, these circles, right? But you can see that this circle occurs after player 1 has played action A, and player 2 then knows that they are at that point where they've seen action A be played, so they now have a choice of playing action W or action X. So you can see that player 2 has certain actions that depend on what player 1 did. And similarly, if player 1 played action B, player 2 could play action Y or action Z. So it's this sort of logical tree structure that shows the progression of a game. These terminal nodes, these nodes down at the bottom, these are the states of the world at the end of our game. So they are situations where our game has ended. And in those scenarios, there are payoffs that are assigned to each of our players. Again, the blue payoffs are going to be for our first player, in this case, player 1, and the green payoffs will be for player 2. All right. So this is just to give you an idea of what the different types of games look like. We will mostly be talking about simultaneous move games, right? And one of the key things about simultaneous move games, and if you've watched the film A Beautiful Mind, you'll know all about John Nash. And so when I talk about the Nash equilibrium, you might think, oh, weird that crops up. Well, the Nash equilibrium was found or sort of developed by John Nash. And if you watch the film A Beautiful Mind, it stars Russell Crowe, it's from about 2001, that tells the story of John Nash. So that is a story about game theory that you might find interesting if you want to have a movie night at some point. But the Nash equilibrium is this notion of how games sort of get resolved. So if we solve a game, it requires finding the Nash equilibrium, which is really just two players mutually having a best response to one another's actions. And we find it by iteratively asking the question, if a player does this thing, how does the other player best respond? So for example, if we were to look at this game where Amandla and Betty have to choose which crops they're going to plant, you could say, if Amandla played maize, so if we look at that row that I've highlighted where Amandla has chosen to play maize, what would Betty prefer to do? Knowing that these numbers represent utility or happiness, a bigger number is better. So Betty will choose a 3 rather than a 2 because 3 is bigger than 2. So what I tell my students in first and second year is I say, draw a circle around your best response, or underline it, or highlight it, or I don't know, draw the Powerpuff Girls around it if you want. Just indicate that that is the best response in that scenario. Then we iterate and we say, well, we now know what Betty's best response would be if Amandla played maize. What would Betty's best response be if Amandla played sugarcane? And hopefully you can see again that Betty is choosing between playing maize and getting that 4, or choosing sugarcane and getting the 1. So we say, well, 4 is better than 1, so 4 is the best response for Betty in that case. We've now gone through everything about if Amandla did this, how would Betty respond? So now we swap our our logic and we say, if Betty did this, how would Amandla respond? And we say, if Betty were to choose maize, would Amandla want to plant maize and get the 1 or plant sugarcane and get the 4? Well, he'd choose the 4, which is better than the 1. And that's then Amandla's best response. And similarly, if Betty chooses sugarcane, then Amandla could choose to plant maize and get the 2 or plant sugarcane and get the 3. And we see that the 3 is the best response in that case. We now look for our mutual best response, so where both players are playing best responses together, and we see that it's in this cell down here, where Amandla plays sugarcane and Betty plays maize. So we would say that our Nash equilibrium is sugarcane maize. We can see that both players are doing the best that they can. We see that the 4 is the highest payoff that they can get. We see that this is the best for society because the total society gets the highest payoff. So this is supportive of the equilibrium concept that you've seen in the past, right? Adam Smith's concept of equilibrium, which tells us that individuals, when they act selfishly, well, they could actually lead us to outcomes that are beneficial to society as a whole. But that's not always the case, right? And this is one of the big things about game theory is if you watch A Beautiful Mind, you'll see a clip where Russell Crowe comes out and he says, Adam Smith was wrong. Adam Smith didn't know what he was talking about. Yes, sometimes we get to a situation where we've got Adam Smith's equilibrium outcome, but not always. And in fact, there's an example which is called the prisoner's dilemma. It's a very common example. You probably find it all over the show. You've probably heard about it. And the traditional setup of the prisoner's dilemma goes as follows. You and your friend have been caught shoplifting. So something small. Maybe you've stolen a chocolate from the local Pick and Pay, something like that, right? And the police have come to arrest the 2 of you. But they've noticed something. They've noticed that the modus operandi that was used in the shoplifting case is very similar to the robbing of a bank a couple of weeks ago that they don't have much information on. So now the police are having a think. They say, you know what? We're going to put these 2, they take you and your friend and they put you in separate interrogation rooms. And they say, if you stay quiet, right? If you and your friend both stay quiet, we've only got enough evidence to put you away for shoplifting. We'll put you away for 1 year in prison. That's the sentence you'll serve. But if you confess and implicate the other guy, then we'll let you free. Like essentially you're turning state witness, so we'll let you go. We're going to nail the other guy though. You confess and tell us how they were involved. We're going to nail them. We're going to get them away for 10 years. Obviously they were the mastermind. We're going to get them. But the thing is, if you both flip on one another, if you and your friend both confess and say, oh no, look, the other guy was the mastermind, the police now have enough evidence to implicate both of you. And they can put both of you away for 7 years. So the question is, what would you do? Would you basically snitch on your friend? And I think it's probably, you know, we might not be proud of it, and I'm not going to necessarily ask anyone to out themselves at this point, but I will put my hand up and absolutely say, sorry, if you're in jail with me, I'm going to snitch on you, right? Because I want to get out. I want to go free. I don't want to go away for a year if the option is that I could go away for nothing. And if I think that you're not going to snitch on me, we're A for away. Then you go away for 10 years. I don't have to worry about you for 10 years, right? But that doesn't sound like the best option, right? In fact, the best option would be for everyone to stay quiet and to just serve the time for the shoplifting. And we can see this if we solve for the Nash equilibrium of this game, which basically sets out this story in a game table form, right? It's simultaneous because you don't know whether the other guy is confessed or not. And you can see that if prisoner 1 were to deny, 0 years in prison is better than -1, so prisoner 2 would confess. If prisoner 1 confesses, -7 is better than -10, so prisoner 2 will confess. Similarly, if prisoner 1 denies, if prisoner 2 denies, prisoner 1 will choose 0 rather than -1 because it's better. And they'll also choose -7 over -10 if prisoner 2 confesses. And we see that we've got a Nash equilibrium of confess, which is not Adam Smith's equilibrium, right? Adam Smith would have said that we should do what's best for society, and by acting selfishly, we should end up over here, where both players are denying, and you see the sort of best outcome for your society. And in this case, I'm talking about society as the two prisoners. I'm not saying society as a whole, because we probably do want the prisoners put away in our normal society. So this is an interesting deviation from traditional economic theory. And it also helps us understand our climate change game. Because maybe if we have the options to go green or to stay business as usual, we can think about going green as having some cumulative benefit per person that goes green. So maybe there's a benefit of 5 per person that goes green, but there's an individual cost associated with it. So there's some inconvenience of going green. You have to learn how to ride your bike again. You have to get fit again. You have to try and charge your car around load shedding schedules. The cost of installing solar panels, all of that kind of thing will impact you. Whereas business as usual means you continue with your current behavior, and there's no individual cost that is incurred right now. Yes, there might be a cost in the future, but it's not really occurring right now. So this would then give us a game table that looks something like this, and we'd be able to see, oh, actually, solving for our Nash equilibrium, the Nash equilibrium would be business as usual, even though the best outcome would be go green, go green. And this might explain to us why we haven't seen more of a move towards greening the economies over time, is because there's just this individual cost that is associated with going green. And you think, you know what, if my neighbor's going to go green, if my neighbor's saving water and they are, getting solar power and they are biking to work, does it really matter if I'm driving my car? Or what difference does me driving my one car to work make? Right? So that's the thought process here. We could see climate change as an example of a scenario where Adam Smith's idea of equilibrium no longer holds. The other thing that's interesting about game theory is that, it breaks away from this idea that there is a single equilibrium. Traditional economics says this is the equilibrium. Here's demand, here's supply, they intersect, this is the price and the quantity, or this is the profit maximizing output for a firm. And that's it. There is one profit maximizing output. There is one quantity of this good that gets supplied. The thing is, in game theory, we're allowed multiple equilibria. Think about which side of the road you drive on, right? So have a look at this game. You could drive on the left or you could drive on the right. And intuitively, hopefully you understand that there is an equilibrium where if everyone is driving on the left, so should you. But if everyone is driving on the right, so should you, right? Because you just don't want to be in a collision with the other people on the road. So here, this scenario allows you to solve for the Nash equilibria, where if person 1 drives on the left, person 2 should drive on the left. If person 1 drives on the right, person 2 should drive on the right. If person 2 drives on the left, person 1 should drive on the left. And if person 2 drives on the right, person 1 should drive on the right. And now we see 2 Nash equilibria: drive left, and drive right, right? So 2 Nash equilibria. That would never have happened in traditional economics. Couldn't be, not possible. Another example, right? So this is what we call an assurance game, for those of you that are interested. Another example would be, let's imagine that you and your partner are trying to decide where you're going for dinner, or what you're doing for date night, rather. You want to go to the movies because you are quite interested to go and see a new film. I don't know. When I normally teach this, there's always something exciting on in the cinemas. Maybe you want to go and see Argyle because you've got a big crush on Henry Cavill, or maybe you want to go and see Poor Things because you've got a big crush on Emma Stone. Who knows, right? But you want to go to the movies, but your partner wants to rather go out to dinner and talk, right? They want to talk about things. They want to catch up on the week. So here we can see 2 different equilibria again, right? If you go to the movies, your partner will want to go to the movies as well, because otherwise, it's a bit of a rubbish date. If you go to dinner, your partner will want to go to dinner. If your partner goes to the movies, you'll want to go to the movies. And if your partner goes to dinner, you'll want to go to dinner. So we again have 2 equilibria. We've got movies, and dinner. And this is what we call a battle of the sexes game, where we've got 2 different equilibria and 2 different agents prefer different outcomes. Now, this is something that could never have happened in traditional economics. Traditional economics would never, ever have predicted that you could have 2 steady states in the world. In fact, and this is like a teaser, if you ever study game theory further, These games actually have a third equilibrium where you allow players to adopt what we call mixed strategies. So where you go to movies some of the time and dinner some of the time, right? There's another, and that would never have flown in traditional economics. Traditional economics says you choose one of them and you just make your peace with it. That is what happens. The one thing that is a little bit tricky, though, is that we do have an equilibrium selection problem. Where you've got two equilibria, how do you choose which one, right? In the driving game, how do you choose whether you're driving on the left or driving on the right? I mean, we've obviously got rules and laws that come up with where we want to end up, right? So we know that in South Africa, we're going to drive on the left, but in the United States, you would drive on the right, and that's just because of the rules, right? But what about the very first people who had to choose which side of the road to drive their horses and carriages on, right? How did they choose left or right, right? And there was absolutely no way to know which one of those two equilibria get chosen. I mean, in our example here, I set it up in such a way that driving on the left is superior. And maybe that's because if you're driving on the left, then the person is sitting on the right-hand side of the car. And then when you're changing gears in a manual car, you're taking the non-dominant hand off the steering wheel for the majority of the population. Maybe that's why it's superior, but it doesn't dictate that's where we'll end up, right? Another example is in the case of the QWERTY versus the Dvorak simplified keyboard. Right? If you have a look at your keyboards in front of you, if you're on a laptop, you'll see the first row of your keys spells out QWERTY, like in this top picture over here. It's the same layout as what you'll find in your phones when you're texting people or anything like that. But interestingly, that layout has been shown to be inefficient. The QWERTY keyboard layout is actually inefficient relative to the Dvorak simplified keyboard. This keyboard over here has been set up in such a way that it improves typing speed by up to 30%. It can decrease the number of errors made by typists involved with touch typing and things like that. But if that is the case, why on earth do we still have the QWERTY keyboard, right? Why is it the QWERTY keyboard that has dominated our lives? And it's all because of historical accident, really. It's all because when people were developing keyboard layouts, both of these keyboard layouts took the approach of separating keys on the typewriter that were often used close together to avoid typewriter jams. When the hammers came forward, you didn't want them to jam while they were hitting the ribbon. But it just so happened that the first touch typing course that was offered on a QWERTY keyboard. So typists and secretaries who wanted to learn how to type and make sure that they were more efficient in the labor market went and learned how to type on a QWERTY keyboard. As a result, firms wanted to buy QWERTY typewriters so that their secretaries would be more productive. And so we ended up, by absolute fluke, we ended up with a scenario that the QWERTY keyboard has just propagated through time, even though it's inefficient relative to the alternative Dvorak keyboard. But it's just too difficult for us as humans to adjust our behavior and change to a new keyboard because of what we call the quasi-irreversibility of investment. It's taken us so long to get used to one keyboard, it's going to take a lot of time to get used to another one. I mean, if any of us have changed from a Windows to a Mac or vice versa, you should understand that feeling. Or getting a new cell phone, if you're moving from Android to Apple or vice versa, learning a new cell phone, you just think for the first couple of days, it's hell. You think, I could never do this. This is crazy. Can't make sense of it. But over time, you get used to it. And it's that first little like bump that makes you feel like it's too difficult to actually change your behaviors. So how do we better understand human preferences or behaviors? Well, we have game theory. And what we want is game theory can help us understand behavior if we know what people's preferences are. And in order to understand people's preferences, we basically use this thing called experimental economics. And I find this fascinating. I think it's super cool. Experimental economics makes use of different sort of tasks. You bring people into a lab and you basically observe their decisions. And you observe their decisions over certain sort of behavioral traits that you want to try and understand. So are people likely to punish others? Cognitive limitations. So I'm sure we've all heard of that riddle where a ball and a bat cost 110 Rand and the bat costs 100 Rand more than the ball. How much does the ball cost? And everyone says, oh, it must cost 10 Rand. But it's actually 5 Rand. And it's because it's 5 Rand and 105. And people's cognitive limitations tend to mean that they quickly calculate these numbers and they use what we call automatic thinking rather than deliberate thinking. We can measure how altruistic people are. How much are you willing to donate to an honesty box? If there's like wine available at a function, would you donate for the drinks, etc.? Would you be willing to pay for aftercare for your children? And you do experiments to try and find this information out. And sort of as a closing point, what I'll say is there's 2 examples that are really interesting. You've got an experiment that was done, because in Israel, there was an experiment where daycares were just getting overrun. Parents were arriving later and later and later to pick up their children. And so in about 2000, 2001, I think, 2 researchers decided that they were going to introduce a fine for late coming to the daycare. They said, if you arrive late, we're going to charge you a certain number of shekels because we are now having to pay staff overtime, or we're having to have staff spend extra time at work. And so they thought that implementing a fine would be able to get rid of this late coming. But in fact, it actually increased late coming because it turned this into basically a price that people are sort of thinking about. They're saying, if it costs me 10 shekels for an hour, how many hours can I afford? Right? So it changes behavior, and that's not behavior we would necessarily have predicted ex ante. Another example is to promote female health. In Zambia, there was a drive to give out female condoms, and there were monetary incentives to say for every condom you give out, you will get 10 US cents, or for every condom you hand out, you will get $1, or for every 10 condoms, or if you hand out 100 condoms, you will get a gold star in your window. And actually, the thing that helped people the most was the gold star in the window, because it suddenly meant that there was the societal status to say, I am proactively supporting women's reproductive health. And that's an interesting behavior that we wouldn't have thought. Traditional economics would have said money is what drives everything. But maybe it's social recognition and social behavior that changes the way that people will behave and allows us to understand people a little bit better. So I hope that that's been interesting. I haven't prepared anything more, but if there are any questions, I am very happy to take them. So thank you very much. I see Mashford. Yes.
Oh, thank you for the wonderful presentation. So I was struck by the idea that people make decisions based not just on their own preferences, but also on their expectations about the actions of others. And I was also fascinated by the way that game theory, it can be used also to model and predict human behavior in wide contexts, whether it be in economics, climate change, politics. So an important question to ask is are there any ethical concerns or limitations associated with using game theory to model human behavior? Thank you.
Great. I mean, that is a very, very good question. And what I'm going to do to answer that question is just separate the 2 aspects that I've spoken about. So game theory in and of itself is just purely the mathematical modeling. So the game theory part of things, there's absolutely nothing no ethical concerns about you sitting with a piece of paper and putting numbers together. Where the ethical quandaries come in, and boy, do they come in, is when you're trying to gather information on people's preferences using experiments. There are absolutely, I mean, it's a absolute minefield. There are ethical dilemmas. I mean, one of the big things is with human behavior. I'm sure we've all heard about different psychological experiments, and realistically, game theory and and experimental economics are really just, psychology that economists have adopted for their own purposes. But we've heard of psychological experiments where, are you willing to increase the pain that a subject is feeling by pressing this button? And, people will carry on pressing it. And those are the kinds of ethical dilemmas that you've got to think about when you try to design an experiment. We tend to, in economics, have a fairly strict guideline about how we go about designing experiments. It should never in any way, cause harm to participants. And that's a very big thing, is it's about a do no harm. We should also not ever be taking on experiments where, for example, you are depriving people in need of a service that is required. So, a field experiment where you build a new clinic in a new area, you can't say, oh, we're going to actively choose to build a clinic here. Even though we've got money, we're not going to build another clinic in another area. You've got to think very carefully about, the people that are involved, because ultimately experimental economics does deal with people, and behavioral economics deals with people. And you've got to make sure that you always conduct any research or any analysis with that lens of, I've got to treat these people with decency. I've got to do no harm to them. And that, the sliding scale of what harm can be done can be very different. But yes, there are loads and loads of ethical quandaries that could crop up, and it's very context specific. But yeah, a very good question, and very applicable to my own research, where I have to do a lot of ethical applications. Yes, I see Jeff.
Thank you.
No, thanks, Rob, for a really, really fascinating lecture. And like Dr. Zenda, I just want to compliment you on it. It was absolutely engrossing. My question is, I guess there must be situations where there isn't a clear mutual best response. And what do you do in those situations? How do you handle that scenario?
Right. So one of the really nice things about game theory is John Nash, he put together a PhD proposal or a PhD thesis back in, I think it was about 1960 odd. And he found a result that was absolutely incredible. And he proved mathematically that every game, no matter what game you've got, there will be some form of mutual best response. Not necessarily in what we call pure strategies. It could be in mixed strategies. So, I mean, think about rock, paper, scissors. If you're playing rock, paper, scissors, if you always play scissors, you know for sure that your opponent is going to be able to take advantage of you. But what John Nash proved is that there is actually a mutual best response in that game. What that mutual best response is for each player to alternate their choices between rock, paper, and scissors, and do each one of those 1/3 of the time, right? And he proved generally, no matter what your payoff structure in the game is, and no matter what your probabilities are, there will be some way of finding a mutual best response, either by people taking one direct action all the time, or by taking actions that are sometimes a little bit, sometimes they this, sometimes they that. It's not always predictable, but over time they sort of take on actions with certain probabilities. And that's the study of mixed strategies. It's something that I teach in the intermediate game theory course at UCT. But yeah, so it's a very interesting question, because actually there's always going to be a mutual best response. It's just that sometimes you need more advanced tools to be able to find that mutual best response.
Got it. Thank you for that.
Thanks, Rob. Very interesting lecture, and it's actually tweaked my interest again in the economics field. So I was going to ask you, where can I learn, or where can we as a group learn more about game theory and behavioral economics?
Yeah, so I mean, where you can find this, one of my favorite things to do is to just look around me in the world. So that's one thing you can do. You can look around yourself and you can see where are people interacting. You know, how do you decide when you're going into an interview, into a job interview? How are you presenting yourself in that interview? How are you presenting yourself in front of a class that you're teaching? So that can sort of pique your interest in thinking about game theory. But if you are thinking about what you might like to read, where you might be able to pick more up. So I would very strongly recommend, if you're interested in the experimental economics, I'm pretty sure it's still on Netflix. There's a show called 100 Humans. And that is an example of how people use experiments in order to gain insights on behavior. So if you're interested in watching a Netflix show about game theory or experimental economics, that is one. If you're interested in reading about game theory, books by people like Malcolm Gladwell, you know, the book that he's written called The Tipping Point, that's all about what we call collective action games and how you can tip people from one equilibrium to another by getting critical mass behind a particular strategy. Richard Thaler wrote a book called Nudge, which is all about nudging behaviors. So how do you encourage more people to, you know, more people to contribute to their 401ks in America, their retirement funds? Freakonomics is another example of a book like that, where you get information about game theory and things like that. I mean, I could go on for ages and ages, but game theory, funnily enough, if you go into your local exclusive books or your bargain books and you want to find a book that tickles that itch or it scratches that itch, go to the nonfiction, the sort of popular psychology section of your exclusive books and have a look to see what they've got there about human behavior. Richard Thaler, Malcolm Gladwell, we've also got Kahneman and Tversky. All of these different people have written different takes on game theory and different takes on behavior that could be interesting to read, maybe as a bit of bedtime reading, or just, you know, to keep yourself up to date with what people are doing in the field.
Thanks, Rob. I've taken note of those, and if I haven't got the names correctly, I'll get in touch with you.
Always welcome.
Okay. Are there any other questions from the rest of the participants on the call? Don't be shy. No, I think that's it, Rob. No more hands are showing. I just want to thank you so much for giving up your time in the evening, and I hope you had dinner, or I hope you're going to have a very good dinner. But yeah, it's really this slot is really typically during dinner time, so I hope we haven't upset your evening too much, but we really appreciate you being available, and a very most interesting masterclass that you've given, and I look forward to it. We all look forward to engaging with you in the future. Thank you.
Thank you so much for having me. I mean, it's been such a pleasure. And if I can also just say to anybody, if you've got any questions, I mean, feel free. I know Jeff and Sharon have got my contact details. If you've got any questions or things that suddenly crop up that you want to discuss further, please reach out. I am very happy to engage. I'm so excited about this. I'd love to have more people converted to my game theory cult, if you will. So please feel free to reach out.
Perfect. Thank you so much.
Thank you. Have a wonderful evening, everyone.
Cheers. Bye-bye.
Cheers.